All right, here it is, Sunday. Exam on Wednesday, so we've still got some time. All right, I've got some general comments. So let's see. I've had it pointed out to me that the notes that I gave disagreed with the book on something. And so specifically, that is major versus minor products and allylic halogenation. All right, so this is the first time I've taught radicals, so I might have had a misconception or two coming in. Anyway, I don't care that much about it, and so what do you think the odds are that you'll need to distinguish major versus minor products from allylic halogenations on the exam? The exam's written and it's not on there, so not a big deal, and this is probably never going to impact you again in your life, so it's okay. Okay, so don't worry too much about major versus minor products, but do be cognizant of the fact that you can get multiple products, right? So it's still fair for me to expect you or to ask you about all the possible products that could form, but don't worry about major versus minor. Let's see. So the exam, I'm happy because it's written, so that's done. A change between my exam and the practice exam. So the practice exams that I've showed you have how many spectroscopy problems on them? 3. I'm a little uncomfortable with there being 90 points worth of spectroscopy problems on the exam because, I don't know, I don't like problems that count a lot in the first place because you can just get crushed. And so I will have 2 spectroscopy problems instead of 3 spectroscopy problems. So we are reducing that down to, I guess, 60 points. So I've had to maybe come up with a few smaller spectroscopy type problem or questions to ask you on the exam. But I don't want that. I just don't want half the exam to be spectroscopy. So yeah.
So we memorized the NMR, like where everything is, but IR we're gonna have a chart, right?
You'll have a chart for both, for all of the spectroscopy. So there's a cover sheet posted under exam 3 on Blackboard. And so I give you proton shifts, carbon shifts, and IR peak shifts. So we'll all have that. I don't want you to spend time worrying about memorizing it. Probably Orgo too, it's fair to expect you to memorize those things. But this is just our little introduction to Orgo, or to spectroscopy, so none of that. And then other things about the exam, there's nothing tricky on it. I don't try to write tricky problems. I want the people that are on top of the material to do really well, and onward and downward from there. So I'm never trying to trick anybody, so I try to write this as fairly as possible. If you know your stuff, you should be good to go. General questions about class? Hope?
What's the difference between IR and NMR?
Yeah, so IR is just that's the one where the baseline's up top, right? And so, and you just have a few diagnostic peaks that you're looking for. And so that's what I kind of introduced to everyone as bonus info. So if you see a carbonyl stretch around 1700 to 1800, you've got a carbonyl somewhere. You know that before you start going in and looking at your proton spectrum. The vast majority of your information will always come from the proton spectrum, but seeing an IR peak that corresponds to a carbonyl or corresponds to an alcohol just gives you a little bit more structural information as you go putting your stuff together.
NMR is when it's on the bottom.
Yep.
The peaks are on the bottom.
Yep. So basically the fingerprint region is the right side. And so what you typically find when you're looking at an IR spectrum, and actually let me go ahead and bring up that cover sheet really quickly so everyone will have a good idea of what we're looking at. Basically we split the IR spectrum up into 2 regions, and so on the left side is typically there's not a lot of noise, there's not a lot of peaks, and so typically there's very strong diagnostic peaks there on the left side. Then on the right side, it typically gets a lot messier. And so in that region, it can be a lot more difficult to obtain information. Certainly, there are ways that you can use that to obtain information, but it's beyond the scope of what we're going to talk about in this class. So we don't worry too much about that fingerprint region on the right side. And so when we look at our cover sheet, there it is. There's the exam. All 6 versions of it that I've made. So here's our cover sheet. So you can see that when we're showing our IR spectrum, our x-axis is usually 400 to 4,000 wave numbers. And so you can see in the IR spectrum that really most of the peaks we're looking at are above 2,000. And so it's that stuff above 2,000 that we've really been focusing on. Anytime, the really common ones are your carbonyl peaks, usually around 17 to 1,800. And so that's just a dead giveaway that you've got a carbonyl. Carbonyls and alcohols are typically the easiest to look at and know exactly what they are. So if you've got an oxygen, chances are you're going to see a carbonyl or you're going to see an alcohol. Really good odds. And then I've just given you a little, this is the majority of stuff we've seen thus far. We haven't had a lot of really complicated spectra. Typically it's been alkanes or some alkenes, or we've had some neighboring oxygens, or we've also seen a little aromatic system sometimes. So that's pretty much all that you should expect. And same for the carbon shifts. Rhea?
Yeah, a question about the chart. So on the IR table, when they say like SP, CH being around 3,300, and then like C triple bonded to C being like around like 2,100,
Yeah.
is that talking about like the first one being that H, and then I guess the C triple one C is just talking about the carbon?
Yeah, and so it's specifically that bond that it's showing that is the stretch that's being measured with the IR spectroscopy there. And so what you got to consider is the fact that, well, in a given alkyne, it could be in the middle of a carbon chain, like this, or it could be a terminal alkyne that looks like this. And so looking back at our chart, we can see that that CH stretch is around 3,300. So we certainly would expect this around 3,300. And then for the triple bond stretch, 2,100 to 2,250. So we'll just say there's this one that we might expect to see around 2,250. But in the top one, well, we don't have a CH bond, right? And so we would only see the 2,250 stretch in that case. So to ever actually see the CH bond stretch in the IR spectrum, we do actually have to have that bond in our molecule. So that is one way you can distinguish between a terminal versus an internal alkyne. Yeah. Yeah.
Do we get the values of the IR spectrum, or do we get a graph?
So that's the one part of the exam I haven't quite gotten finished yet. I'd like to have you be able to have a spectrum in front of you to get the information from. It can be a little challenging at times because real life spectra aren't often very clean, and so I don't want there to be any misleading information. So if I think there's anything that could basically screw you guys up, I'm just probably going to list the peaks. But the proton spectra, I've gotten clean. In fact, I've just made my own custom proton spectra corresponding to the molecules on the spectroscopy part. So those are going to be crystal clear, really easy to distinguish. Yeah.
Do you know how to calculate enthalpy for radicals?
We didn't cover. So, yeah.
Would we need to know like multiplets and like overlapping doublets versus triplets and things like that?
The only thing we've really talked about when it comes to coupling constants is how it applies to doublets of doublets. So let's just actually, now that I've got you all here, let's look briefly at kind of what's going on. So there's two types of systems. Let me see if I can copy this. So there's two types of systems that we've kind of talked about in terms of coupling. And so over here on the left side, we're just going to have some alkane stuff. Now we've learned that when we have alkane stuff, we can use the n+1 rule, right? And so this is why we can use the n+1 rule. So protons A here being split by protons B, and so following the n+1 rule, what kind of multiplicity would we expect? We would expect a quartet, right? 3 plus 1 is 4 peaks. Here's why we see 4 peaks, and this is why we're able to follow the n+1 rule. So what happens is this initial signal of protons A is they're going to get split 3 times. All right, and so what it is because because all of these B protons are equivalent, they're going to have the same coupling relationship with A. So what happens is these 3 protons here are going to split the A signal 3 times, but by the same amount. And so that relationship, I've just come up with 8 hertz. So what happens is the signal is split once by 8 hertz, and so you can see it's split into 2. And then those 2 signals are split again a second time. Now what happens is as this signal goes left, and this signal goes right, you can see that there's overlapping signal, right? And so that's why in a triplet, we end up seeing peaks that look kind of like that, where the middle one has twice as much area. It's because basically that's really 2 signals that are just overlapping. And then what happens is finally they get split a 3rd time, and again, what you're going to have in the middle are overlapping peaks. And so because that each time these signals are being split, they're being split by the same amount, that 8 hertz, we end up with the middle peaks being overlapping, and we can follow the n+1 rule. Now the one case we really looked at in class where we didn't have that is in a triple bond like this. And so of course protons A, B, and C are all going to be chemically equivalent because they all have different relationships in this structure. And so when we just think about A, what we're going to have is splitting between A and B, but we're also going to have splitting between A and C, and because the relationships are different, those coupling constants end up being different as well. So what happens is A is going to be split, say, by the C proton at about 15 hertz, and so that turns into 2 signals. And then those 2 signals are going to get split from the 6 hertz from the AB coupling, but you can see that now, instead of splitting by the same amount, we're going to split by a different amount. And so by doing so, we can now see both of the inside peaks, right? And so that's why we end up seeing a doublet of doublets for alkenes. We can't follow the n+1 rule because unlike this just simple alkane system where the middle peaks basically overlap, we don't get that in the double bind. So that's really the only case where we've seen any of the, or we've really talked about multiplicity like that. Oh.
Can you draw a doublet of doublets? What does it look like?
Pretty much right here.
Like you have the triplet over there, but if you were to draw it.
Yep, and so let's, all right, so over here, what we would end up with is a quartet, and that should be, I think, 1, 3, 3, 1. So our quartet would look like that. And then our doublet of doublets would look like that. And so you can see looking between the quartet and the doublet, those are clearly 2 different types of structures, right? This clearly does not follow Pascal's triangle, and so you should be pretty easily able to distinguish between a quartet and a doublet of doublets. Yeah?
I think there's one like this on the exam. Can we go over it?
Which exam?
It's number 3 on the 2015 exam.
And so are there any other general questions about exam on Wednesday? We'll have office hours both Monday and Tuesday, so there's still time left to get in touch. All right, so number 3, yeah. So what you're looking at is some peaks in that alkene region, right? So we see those peaks are kind of between 5 and 7 or so. And so this is clearly going to be an alkene. And so what that does is that definitely goes ahead and rules out a few things. So number 1, we don't know from just looking at it maybe how many alkene peaks there are, but what we can say is it's clearly not this alkane system, right? Because that's not where the shift would be for that. It's clearly not this benzene, and it's clearly not this benzene, because again, those would be further downfill in the 7 to 8 range. So really it comes down to 2 things, and so you can see that one is an alkane, or I'm sorry, an alkene with 3 protons, and then this one here is an alkene with 2 protons, and then a neighboring proton right here. And so what we've got to do, and really the distinguishing information here is when we look right here, this can be either one doublet of doublets, or it can be 2 small doublets of doublets, where you can't even see the second doublet within there. And so one thing that you can tell is that when we look at the gap between each of the doublets, is it the same or is it different? It's different, right? And so anytime we have a doublet of doublets, the gap between the 2 is going to be exactly the same. And so what it tells us is that we're not looking at just one signal here, we're ultimately looking at 2 signals. And so we've got 2 there, 1 there.
Doublet, it's 1 signal.
What's that?
Is a doublet of doublets 1 signal?
Yep. And so what we see is there are going to be 3 alkene protons, and so there's only one answer that can be that. So it would be B where there's 3, and not the alkene where there's only 2 alkene protons. So that one takes a little. That one's a tougher problem because you have to really get in there and think about what the doublets is going to look like and split that. Yeah.
Can we look at number 2 right about that one?
Sure.
How can you tell the difference between option B and D from looking at that spectrum?
All right, so we'll just, let's see. Let's go back and we'll just do it from scratch. So when we look at this, and this is good IR practice, the one thing I see right here is that there's a peak right around 16 to 1700. And so that's always indicative of what? That's a carbonyl. And so we know immediately that we've got a CO double bond stretch, and that rules out A, C, and E immediately. So then it's just between B and D. And we didn't talk about this much, but it did come up in lab, and I know that I did say something about it briefly when we were going through it in lecture. And so this peak right here, what does this correspond to? That is your NH stretching peak. Now, how many of them are there? We can see there's 2, and so what the distinguishing factor is we see that there's a peak here and a peak here. And so what that tells us is that there are going to be 2 different NH stretches. And so then at that point we need to make sure we're choosing a molecule that has 2 NH bonds, and so that rules out B and leaves D. If there were only 1 NH stretch, you would see a peak that just looked like that, and if there were 0, you wouldn't have anything, right? That wouldn't exist. So that's the distinguishing factor there.
The main difference between the OH and the NH is how broad it is, right?
Typically, yeah, so the OH is typically going to be broader than an NH. I think it'll be fairly easy to tell because in an OH stretch, we're talking about something that is going to probably look more like that.
Okay.
I don't think it's typically as intense of a peak. It's maybe shorter and broader. Yeah. Number 4 on the second handout, is that 411? Okay, so number 4, this one? One of the NMR handouts. Okay, yeah, let me track that down. Let me find it. Are there any other big exams this week? No?
Turning in a paper.
Yeah, I know the last one I seemed to line up with pretty much every exam in existence on this campus.
Luckily, bio doesn't have any more exams.
Yeah. All right, so number 4, you mean this one? Was it number 2? See if you can track it down, specifically the one you've got in mind, so we can do it. Yeah.
I got all my stuff.
Yeah.
Can I ask another?
You can ask another question. Yeah.
On our practice exam from 2014.
2014.
8.4.
8.4.
Yeah.
Yeah. So in this case, we skipped past the thermodynamics of radical reactions, and so not fair game. Won't be on
Does that
that.
apply to A3 as well?
That does apply to A3 as well. Yep. Yeah. Oh, is that from lab?
Yeah.
That's number 3. is week 1 or 2? 2. Okay, so what we want to do. There's a chance this is going to end up upside down, or on its side. It's going to make me so mad. Or I guess if it's already on its side, it is what it is. All right. Yes. So, I'm sorry. You just got to turn your head. It's just how it is. Okay, so looking at this thing, we've got C4, H12, N2, and again, I'm very sorry, but I have spent like an hour in the past week trying to figure out how to rotate documents in OneNote, and what happens is I click on the document, I come up here, I say, let's see, here we go. There's no rotate. There's just no rotate whatsoever. Move just moves.
Can you do it? Is there a keystroke that'll let you turn it? That'll turn that thing you're holding into an arrow?
I have no idea.
That's how it works.
So here, see, it even up here, the rotate is grayed out.
I guess you just can't.
So I don't know. Anyway, it's Microsoft. What are you gonna do? Okay, so let's go ahead and first get our IHD. And so this actually gives me a good chance to talk about how some things will work. So for one thing, on the spectroscopy problems on the exams, there's going to be 2 boxes, okay? So one box is going to say final answer. It might not say final answer. It'll just say answer. Don't want it to sound too game showy. And then another box. What's that? What? Yeah. And then so the other one is going to be have something along the line of clues. And so that's going to be your opportunity for partial credit. So these problems count a lot. They're like 30 points. The only way you can get 30 points is by getting the final structure. But you could get 20 or 25 points. I don't know how I'm grading it yet. And so basically that's going to come down to clues. What have you been able to figure out about this molecule? One of those clues would be, say, the IHD. And so in the IHD, of course, it's 4 times 2. We add 1 for nitrogen, is that right? Yeah. So plus 1, I'm sorry, plus 2, minus 12, and then ultimately plus 2 just as part of our formula. And that's all divided by 2. So here we've got an IHD equal to 4, 8, 10, minus 2, 0. So we've got an IHD of 0. What you want to make sure you do tomorrow, or Wednesday, surprise. What do you want to make sure you do on Wednesday? Tell me that. Tell me you've got an IHD of 0. That's a little bit of information about that molecule that I can give partial credit for. So basically, anything that will help lead you to the final structure, or at least things that are pieces of clues or clues from the information, put it in the box so that I can give partial credit. So IHD equaling 0 would be 1. Okay, so let's see, another clue that we might have is down here we see there's a peak that it says is exchanges with D2O. What does that mean? It's either an OH or an NH. Which can it be here? Only an NH. And so what we've got here is clearly we're going to have some form of NH bond. And so show me that. Tell me that that exists in the box so that I can help, give you some partial credit as we go, because there's going to be cases where you're trying to solve these spectroscopy problems and you can't get the final structure, but I bet you can pull a lot of information out of the spectra regardless, and so that's where I can help assign partial credit. Okay, so looking at our spectrum, do our integrations add up to the number of protons?
No.
It does not. So really what we're finding is that's 2, 2, 6, and 2. Okay. And so does that make sense? Do we see an IR peak corresponding to NH protons? Yeah, we do right here. And so furthermore, how many peaks are there?
2.
There's 2, and so we expect there to be 2 in H-bonds, and in fact, that's what we see. This is all good information. Tell me in the box that you need to double this, right? Any piece of information that is going to be accurate in helping us determine this structure, tell it to me. Let me know. Okay. So then we look at our structure, and let's see. I don't know. What do you guys think? Where are we going to go from here? You can't really read it very well, can you? So, let's see. We've got this peak right here that is downfilled at about 6, and furthermore, it's a singlet. So, can it be next to, say, a CH2? It's probably not next to a CH2, right? So we have a couple of methyls, and so they seem to be equivalent methyls, and they're downfilled. Do we have anything that would cause basically our protons to be shifted downfilled like that? Yeah, we've got a nitrogen, and so I'm thinking maybe what we could have is we could have 2 cases where we have a CH3 and a CH3 connected to a nitrogen. We don't know what's on the other side of the nitrogen, but that seems to make sense given the fact that we have a singlet right here. Okay, so, from what I remember about this structure, these are both triplets.
Yeah.
Yeah, all right, so, and again, this just doesn't show up very well. But what we've got here is a triplet here and a triplet here. Now, does it make sense that those things could be near each other? They pretty much have to be next to each other, right? We have 2 signals that are being split, and so there's 2 signals being split total. They have to be splitting themselves. And so in this case, I'm thinking we would have a CH2 connected to a CH2. So let's call this peak A, B, C, and D. And so here we're going to have our C, and let's go ahead and just say that's A, and that's B. And so integration-wise, it makes sense. This would be a CH2, this would be a CH2, and so furthermore, they would both be split into triplets. Now, let's see. They're not chemically equivalent, so there's not going to be a ton. There might be some symmetry in this molecule, but not a ton. So where do we want to go from here? Well, they're both pretty downfilled, right? Indicating that they could both be connected to what? A nitrogen of some kind. So let's say we've got a nitrogen here, and we don't know what it's connected to. And then there's a good case we have a nitrogen here, and we don't know what it's connected to. All right, so clearly one of these nitrogens has to be this nitrogen, right? There's only 2 nitrogens. So that gives us a little more info. We can go ahead and add these together. So if we add these, we end up with nitrogen, CH2, CH2. And so we're left with this. So how many atoms do we even have left? Just 2 hydrogens, right? Where are those going to go? Those are going to go on the nitrogen, right? We know that there had to be an NH bond of some kind. And so what we end up with is a structure that looks like this. So let's see, our carbon spectrum lists 3 peaks. So how many, that means there's going to be 3 sets of carbons. Does that make sense? Yeah, because these 2 right here are chemically equivalent, and so they account for the singlet in the proton spectrum, and so this seems to make pretty good sense to me. Yeah?
I think that some of like the exams they were saying, like if you have your bases, make sure you don't exceed the formula given. Like, would you, I guess, count off for that?
Gosh, I'll probably be better prepared to talk about that tomorrow in class. I've never given an exam like this, so I've also never created one. So, yeah.
I know when I'm working on these, I need like a lot of space. Are we allowed to bring in like blank sheets of?
So it's funny you say that. I want to make sure you have lots of space. As of right now, the exam's like 7 pages because I'm just giving lots of space. I feel like I should cut that back to 6 in honor of Earth Day, and so I'm going to try. I'm going to play around with space. There's also a chance I'm going to cut out some of the earlier stuff, and then that gives me more space as well. But yeah, keep in mind that so you've got the cover sheet that you can write on all that you want to. So yeah, you should have enough one?
Because I mixed up the major and the minor.
Yeah, and I think you mixed up the major and the minor because that's the way I taught it to you. So it's a nice job. Needless to say, I could ask you for what answers or what products would be possible, but I'm not going to ask you for major minor products because, again, I clearly didn't even know what I was talking about.
Is that also?
Question about stats? Yeah.
Would you be willing to go over the difference between allylic halogenation with NDS and radical addition of HBr?
Yeah, so we're going to talk for a minute about the difference between a standard radical halogenation and then an allylic halogenation. So in your standard halogenation, what we do is we can take an alkane like this, and so we're going to react it with Br2. What does there always have to be for a radical reaction?
Light.
There's got to be light. So we've got to be able to, it's ultimately some more advanced stuff, but we've got to have light. We've got to be able to excite our electrons a little bit. So that's what's going on. And so if we're asked to draw the product that can result from this reaction, where do we start? Most stable radical or weakest CH bond. Same thing, right? And so we look on here, what's the most stable radical we could form? It's going to be the tertiary radical, and so we know that we're going to go through a radical that looks like this. And so from there, we pretty much know that we're going to stick our bromine basically where our weakest CH bond was. So more or less in a typical radical halogenation, the weakest CH bond gets replaced and turned into a CBr.
And is that plus an enantiomer?
In this case, it's not a chiral center because it's connected to two methyls, and so it would just be this one product. Haley, you got a question about this?
Yeah, so there were some practice questions that wanted like the full arrow pushing, including the termination step.
Yeah.
Can we go over the termination step / what we need to know that?
So, the only thing that I've pretty much ignored the termination step. The only thing you want to think about when it comes to the termination step is just knowing that you have two radicals and they're going to obliterate each other and there's no other radicals left. So for the termination step of this reaction, we will have gone through a bromine radical and we will have gone through this alkyl radical. And so there's three possibilities to combine these things, right? We can either recombine two bromines, we can recombine two of these, or we can mix them. And so a termination step can happen at any time, assuming that you have two radicals somewhere. And so just smash them together and you're done with the termination step.
So that last product is the product of the termination.
Yeah, so are you talking about this?
Yes.
So that is the product of, you can make that in a termination step. It's not where you do make most of this. You make most of this in your propagation, but it is possible to also make that in a termination step, yeah. And the reason for that is in the propagation step, what we actually do is we react our radical with bromine like this, such that we produce our product, and then we produce another bromine radical so that it can go back and start over the propagation. So basically, the easy way to remember the three, an initiation step, you have an increasing number of radicals. A propagation step, you end up with the same number of radicals, and a termination step, you decrease the number of radicals. Yeah, that's the big difference between the three. Yeah. Sarah?
Can we do number 3?
Hold on, let's let me do this. I'll come back to you. Okay, so this is just your standard radical halogenation reaction. And so what we can also do is we can do an allylic halogenation. And so in that case, let's see. Let's say we have this double bond. Now let's change it to this double bond. And so in that case, what we can do is we could react it with bromine, right? Same conditions. And so what's going to happen in this case?
Isn't it NBS?
Yeah, but what would happen in this case? Yeah, what you're going to end up with in this case is going to be an electrophilic addition reaction. So you're going to end up with this plus enantiomer. And so that's no good, right? Because we're not doing a radical reaction. That's just an electrophilic Br2 here. That's just an electrophilic addition reaction that we did last chapter. We know this already. So instead of using molecular bromine, what we've got to do is use something that avoids molecular bromine, and so that is what? NBS. That is NBS. So we use NBS in place of molecular bromine, and so we end up seeing a different product. Okay, so in this case, what we end up doing is we can form, let's see. So what we're going to do is, again, we're going to look for the most stable radical, or the weakest CH bond. What is it in this case? Again, it's the tertiary, right? So what we have is this CH bond, and so that's going to be the weakest. So what that does is it means we're going to go through a radical like this. Now, what's particularly stable about this radical? Yeah, it's allylic, right? So we have the possibility for resonance. And so what we can do, show a resonance structure. So how many carbons on this resonance stabilized radical actually have radical-like reactivity? We have 2 carbons that can act as a radical. And so what can happen is we can certainly form both products resulting from that. So one product would result from reactivity at this radical. So that puts our bromine there. Or we could have reactivity resulting from this resonance structure. And so in this case, we would have 2 possible products. Would I ever ask you for major or minor? No, because I screwed that up. So,
There's a double bond.
yes, you always want to make sure you remember that double bond. Yeah, and an allylic halogenation, since we're swapping out an sp3CH bond for an sp3CBr bond, nothing ever changes about the pi bond. That stays the same. Or at least it goes somewhere based on the resonance structure that the reactivity is taking place with.
What's the difference? Like, what is like qualitatively? Between the allylic and the...
So, you know, there's a few differences. Mechanistically, they're completely different, right? Because we use NBS, and so in this case, we're reacting with molecular bromine in our mechanism. We learned how in this mechanism, we do eventually make a little molecular bromine, but not much.
No, I mean like between the regular halogenation and the allylic halogenation. Because like you end up with the same, one of the same products. Aside from the double bond.
Yeah, I mean, that's a pretty big difference, right? We end up with different products.
So like that product, is, aside from the double bond, it's the same.
But that's a big difference.
But
That's a complete functional handle with
but you
which we
also
can...
started with a double bond, so like you didn't actually add it differently, I guess, is what I'm saying.
Right. So again, basically, it's a different reaction because we have a different functional group. We have a double bond, which requires different reagents to go through a different mechanism, and so it's just different. Yeah. About this?
Yeah.
Yeah.
So, what about in the case where you're using the solvent with the R-double-O-R?
So it's not a solvent, but it's going to be a reagent, but it's a peroxide, right? And so in that case, that basically leads us to our third type of radical reaction. So let's go ahead and let's just say we're making a little chart, kind of, right? So this is our first one, and then this is no good because this is actually an EA reaction. Ooh. So this is number 2. And so finally, we could also do our third reaction. And so our third reaction requires peroxides. So we can use the same starting material. And so this third reaction is actually going to be, we're now reacting with the pi bond. We haven't done that in the first 2 reactions. We've been replacing an sp3CH bond. In this case, we actually are going to mess with the pi bond.
What is this called?
This is the radical addition of HBr to a pi bond. That's not a very good name, is it? I don't know. I'll let you come up with a name. I'm not sure that I have a good one for that. All right, so let's think about what can happen here. We're going to add HBr. What's the product going to be? This one is not going to be anti-Markovnikov because it's just HBr, right?
HBr. I'm sorry, I was thinking.
Yeah, I know. I set you up for it. All right, so in this case, this is another reaction that we know. This is going to be an electrophilic addition. that results in the Markovnikov addition of HBr. Alright, so this is an electrophilic addition. We've already seen that one. So that's kind of similar. So in the second reaction, we have to do something special to avoid the electrophilic addition. In the third reaction, we do as well. And so what is that thing we do?
You use peroxide.
Yeah, we want to use peroxides. And the reason that we have to use peroxides is just, again, the electrophilic addition is just faster. We have to figure out some way that we can make this bottom reaction take place. And so what we've found through years of research, I guess this is probably actually known a long time ago, is that if we add some peroxides in there, and that completely changes the mechanism of the reaction. And so in that case, the way that this mechanism works is that we're gonna form peroxides. So we're gonna have the same starting material because it's not involved in the initiation step. But what is involved in the initiation step is the formation of this radical right here. So we basically form two of those peroxide radicals. And so in this case, what we're gonna do is
And where did the HBr go?
so the HBr, I guess, hasn't really gotten involved yet, has it? Let me make sure I'm telling you this right. Okay, so we have this OR radical, and so geez, is this the right mechanism? So in this case, let's see. We have to extract an HBr. Yeah. So actually, what I think it is we make our OR radical. So basically, let's just draw the mechanism so we're all fully up to speed on this. So we start out with our initiation step. And so our initiation step, we have ROOR. So we hit that. Of course, what are we missing from this reaction? Yeah, we gotta have some light in there. So there's our light. And so bam, that's what we get. All right, so we formed two of these radicals. And so that's it. That's our initiation step. We had no radicals, now we have two radicals. We created radicals. So the next thing we do is we go to our propagation step. And so it's in this case now, we're going to take our radical, oh man, yeah. And so what we do is we react that with HBr. Okay, now, so this is our propagation step. So what happens is we're going to abstract this hydrogen from HBr as such. And so what we end up with is just an alcohol, which that's kind of boring, but then we also have a bromine radical. Okay. So from there, what we're going to do is take our starting material, which can react with a bromine radical. And so now it reacts with the pi bond. Now it can react at either position of the pi bond. It can react at the primary position or the secondary position. Which does it add to? It's anti-Markovnikov, right? So it actually reacts with the primary carbon as such. And so that's why we see the anti-Markovnikov selectivity. And ultimately, so let's see what we have at this point. We're going to end up with, let's see, this radical right here. And the alternative, so this would be our anti-Markovnikov product. Our Markovnikov product that we've seen in our electrophilic addition would look like this. And so this is our Markovnikov. And so which is more stable, the anti-Markovnikov or the Markovnikov? Yeah, it's the anti-Markovnikov, and that's just because that's the more stable radical. And so this would be more stable radical. And so from there, I think we just then, from here what we do is we react with another HBr molecule. so what we'll do is we'll basically do this, which gives us our final product, our anti-Markovnikov product, and it regenerates our bromine radical, like this. And so one change we need to make is this right here. So we don't actually go back, this is actually the beginning of our propagation because we're generating a bromine radical. So our bromine radical in this case goes back to here. The most important part of this is just knowing that you're going to get the anti-Markovnikov product. So these radical mechanisms get a little funky. Questions about that? Yeah.
So we're using 2 HBRs.
Seems to be the case in this one, yeah.
Okay, so that's not a problem.
You can always assume that you've got excess HBr.
Okay.
Yep. Yeah.
Is there any way you could show that reaction using a ring?
Yeah. So just some cycloalkene of some kind? Yeah, so in that case, let's say we had, do you have something in mind or you want me to come up with something?
There was a few in the homework.
From the homework I gave you?
Yeah, that was on the 407 one that has like rings.
So which one?
I mean, I don't.
Yeah, so in this case, we'll do the second one. So this one right here. And so it's the same thing. So basically it's going to be the anti-Markovnikov addition of HBr to that double bond. So when we look at that double bond, we see that we've got a tertiary carbon and a primary carbon. So ultimately the bromine's going to end up on what? So if we're adding an anti-Markovnikov, it'll end up on the primary, and so that's what we see. So in this case, we've got an exocyclic double bond that gives us this anti-Markovnikov product. We could also have the double bond in the ring. And so in the case that I've given you, it's just cyclohexene. And so there's no difference between those two carbons, right? So whether you add to the top carbon or the bottom carbon here, you're ultimately going to end up with an achiral product there. So there's still only one thing you can make. Yeah. Does that help? Okay. I missed some. Ria, you were up earlier.
In the allylic halogenation one we did right before, could you explain like with that first step with the hydrogen? Could you draw the mechanisms of that?
Yeah. Okay. So if we go a little more in depth on the allylic halogenation mechanism, let's see. And one thing I will say is we kind of blew through that section, and I tried to make the points correspond to how much time we spent on something, right? So we're going to have 9 days of lecture, and we really just spent 1 on radicals, so expect, similar amounts of points for that. Okay, so was the question how do we go from the beginning to the intermediate?
Yeah, like just like the...
Yeah, and so we have NBS, and so what happens is we react our NBS. So that looks like, and again, you're not responsible for the structure of NBS or anything. So NBS looks like this, and so we hit that with light, and we get homolytic cleavage, and so that propagation step is going to give us 2 radicals that look like that. And so from there, what happens is our bromine radical will, let me make sure I have this right. Yeah, so then the bromine radical will react and basically do a hydrogen abstraction like this. And so what you end up with is then that intermediate that we have above. And so I also mentioned in class, ultimately what happens is because we have to end up with a bromine radical of some kind, right? And so we used our bromine radical here, and so we need another bromine radical basically to react in these 2 steps. And so mechanistically, I said not to worry about it. Essentially what happens is if you have NBS and you have HBr, and so we do produce some HBr in this reaction, right? We produce it right here. So this would be plus HBr. What happens is then you make a little bit of molecular bromine. Actually, so that's what it is here that reacts. Is molecular, and you don't need to worry about why or how that happens. Yeah, that's pretty in depth. Chances of that being on the exam are pretty slim. Sarah?
So how should we, would we just not be asked to do the error pushing mechanism?
I'm much more interested that you be able to give me products than you be able to draw a mechanism. Yeah, I mean, we just didn't spend enough time on radicals to really put a lot on the exam. Yeah.
Can you go number 9 on the 2014 exam?
9 on 2014.
Yeah, the second reaction.
Yeah, and so in this case, what we've got is we're going to react some alkyl halide here with ethanol. And so this is probably not going to be a radical reaction because we don't have any light, right? So this is going to be either SN1 or SN2. So this is going to be one of those cases where we have to predict whether or not we've got SN1 or SN2. So we look at our alkyl halide. What kind of halide is it? So our carbon that's connected to our halide, what kind of carbon is it? It's a secondary. Does that allow SN2?
Yeah.
Definitely. And so we want to do SN2. We're looking for reasons not to do SN2. So we could definitely do SN2 there. So then we look at our nucleophile and we see that it's ethanol. Is that a good nucleophile? No. So we have an uncharged oxygen. So we have a weak nucleophile. Can we do SN2 with a weak nucleophile? We can't, and that's a bummer. So that means we're going to have to do SN1. We've looked to see if we can do SN2, and we can't, so we're forced to go SN1. And so that mechanism, of course, starts with heterolytic cleavage of the C-Br bond to give this carbocation. And so from there, what we're going to end up doing is adding our nucleophile to that carbocation from both the front and the back. And so we end up with these two products here. Yeah.
Can we go over the next reaction on that problem as well?
Yep. And so the next one, we've got NBS and light. What does that scream out in terms of reaction type? That's radical, right? It's almost certainly going to be a radical reaction. So we look there, we see NBS, and so we know that in an NBS reaction we're going to be doing an allylic halogenation. And so in this case, we look for an allylic proton, which we're certainly able to find. And so what we do is we can imagine making that allylic radical right here, which has, of course, reactivity both at this carbon as well as this carbon. And so following our arrows, let's see. Yep, so we've got two possible radicals here. And so we're going to end up with 3 products. 2 of the products will come from reactivity here because we can create a new chiral center. So that gives us this product and this product. Or we can have reactivity at the primary radical, which would give us this product. And again, I wouldn't ask for major, minor. I would just ask you for possible products. So you would list all 3. Yeah?
In the ethanol one, wouldn't there be hydride shift?
There could be. Yeah, so remember, I didn't write these problems, nor have I ever tried them. So, yeah, I guess there could be a hydride shift. So let's say you could undergo something like this, which would lead you to a tertiary carbocation. And so from there, you could end up with also OCH2, CH3. But, honestly, in these sorts of problems, I don't typically expect you guys to just always assume there will be shifts like that. So I usually try to point you that way if there are ever going to be shifts. I try to make it explicitly clear, hey, there could be a shift. What do you think could happen? So, yeah, that's also, I guess, a product they could form. Questions about this? Yeah.
So can you explain why for SN1 you can tap from and back?
So it's because you're going to go through a carbocation intermediate, right? And so if you have a carbocation intermediate, it's sp2 hybridized, and so geometrically it's planar, right? It's trigonal planar. And so what you have is ultimately you end up with, you know, a plane. And so if we have our planar carbocation, we could come in and attack it from this side, or we could come in and attack it from this side. And so you get both of those as a possibility.
And so for SN2,
Yeah, for an SN2 reaction, you're going to have a leaving group on one side, and so we have to do a backside attack. And so our incoming nucleophile comes in from the backside of our leaving group, and it's because it's a concerted mechanism. So we only get one of the possibilities, whereas if it were going through an SN1 mechanism, you could act on both sides. Yeah.
I think this one is similar. Can we do number 1 on 2014?
1 on 2014. All right, so let's see. Yeah, definitely. So we look at this. We've got, what kind of alkyl halide? What kind of carbon is it?
Primary?
It's a primary. Can we do SN2?
No.
Yeah, we can do SN2 at a primary, right? We love doing SN2 at a primary. So yeah, we can do SN2. So then we look at the nucleophile. It's methanol. Is that a good nucleophile or a weak one? That's weak. So we have, again, a weak nucleophile. Can we do SN2? No, so we have to do SN1 because of our weak nucleophile.
Does weak nucleophile always trump the other one? Like, if it's a primary, then that like is definitely SN2, but...
Well, so in this case, we've got to think about a few things. So first off, let's say we have a weak nucleophile. And so what that tells us is there can't be SN2. We're not going to do SN2 unless we have a strong nucleophile that can come in and force the concerted reaction. So the only thing that we could possibly do is what? Yeah, so we have SN1, right? Now we look back at our alkyl halide. We have a primary alkyl halide. Can we do SN1 at a primary alkyl halide? Not really a primary, but in this case, is this a typical primary alkyl halide? Yeah, so what it is it's going to end up forming an allylic cation, right? So typically not at a primary alkyl halide, but we did learn specifically that with an allylic system, so basically if we start a reaction, we're going to end up with this carbocation. This is a particularly stable carbocation because of resonance. And so what we end up with is a resonance stabilized carbocation like that. And so because it's a resonance stabilized carbocation, that does allow us to do an SN1. So it's resonance stabilized. And so what we expect to see is SN1 is allowed. We also said that a benzylic primary alkyl halide is also allowed. So if we had a system such as this primary alkyl halide, that would also be fine because, again, we've got a resonance stabilized carbocation that would result. Okay, so we're going to have reactivity at both of these positions because both of them have carbocation-like tendencies, and I'm actually really curious to see what the answer is. I'm hoping that it ends up being E.
That's what I said, but it's D.
Now that one I actually have a problem with.
That's what I was confused.
Yeah. Again, I mean, rest assured that there's not going to be a problem on here that requires you to do that. But yeah, while I was wrong on the radical one, this one I don't know. I feel like it should be E. Anyway, it doesn't matter because you're not going to be asked that kind of question. So what we have is reactivity at both. And so if we have our bromine react at this one, we're going to end up with this product. And so if we have reactivity at this carbon, we're going to end up with this product plus what? Yeah, plus an enantiomer. Yeah, I mean, it's interesting to me that they have D as the answer here, because certainly, this is going to exist for some amount of time, and so between these carbons, the secondary and the primary, which is going to be the more important contributor? The secondary. So there's going to be more charge buildup at the secondary. So, yeah, again, we don't have to worry about it, but I would expect the secondary to form more of the product. So, yeah. Oh, I'm sorry. I've got kind of bromine on my brain. We've been doing a lot of those, so sorry about that. We do so much bromine with radicals. So yeah.
Can we move on? I have another question.
What's that?
Can I ask another question?
Yeah, are there any other questions about this? Again, it's mainly going to be most important that you know multiple products can form. Don't worry too much about major versus minor. Yeah.
Can you do the last problem on this exam? It's a spectroscopy.
Yes. All right, so we're going to do some spectroscopy. So the way I would start this out, and this is what your exam's going to look like. I mean, you're going to have this is your clue box, and then that's your final answer box. And so the only answer that gets full credit is the correct product there, but you could also get lots of partial by having good stuff in the pieces and constraints box. Okay, so let's see. The first thing I would do is start with the IHD. And so that's going to be 9 times 2 minus 10 plus 2 divided by 2. So that's 18 minus 10 is 8 plus 2 is 10 divided by 2 is 5. All right, so I'll go down here and say, hey, I think we've got an IHD equal to 5. Oh, actually, there's something right there. All right, 5. So, I don't know. What do you think? What's up next? Where are we going to start? Yeah, so we've got an OH possibility, and so it also looks like, I can't tell exactly what these numbers are, but it looks like we could have a carbonyl peak here. I just can't read those numbers. Okay, so that's definitely going to be a carbonyl peak, so we've certainly got this, and so we've also got this broad peak right here, which is pretty indicative of an OH bond of some kind. So we can also say that we have an OH bond. Now, again, I cannot read these numbers at all. So we'll leave that as is right now. Okay, so then what else? What other pieces of info do we have?
You know there's probably an aromatic ring.
Yeah, so we've got 4 protons shifted down into this segment, right? And so that's indicative of 4 aromatic protons. So that tells us that we're probably going to have some sort of aromatic system. And so let's see. We've got multiple peaks. So we've got, and in fact, this says that there are overlap. I wouldn't give you anything that's like overlapping peaks. That's not fair. So I wouldn't get, mine are going to be probably a little easier than this. You should be able to see every peak as necessary. But basically, you've got overlap signals, so you've got 4 different kinds of peaks, and so furthermore, we've got 4 total benzene protons. So how many substitutions are we going to have on our benzene? 2, right? It's going to be a di-substituted benzene, and so we have to think, is it going to be ortho? Is it going to be meta? Or is it going to be para? And so the fact that we've got 4 signals says that it's definitely not which one? Para. It's definitely not para, because we'd only expect 2 proton signals. So really it comes down to ortho versus meta. Okay. And so if it's ortho versus meta...
The one would need a singlet, but we don't have any singlets, so...
It doesn't look like we do, right? Yeah, I mean, unless one of these is a singlet, but it doesn't look like that's the case. And so it looks like probably what we've got here is another doublet and triplet. That's the only thing that would make sense. So most likely what we're going to have is this ortho substitution, because if we had meta, we'd have to have a singlet somewhere in our benzene peaks. Okay, so let's see, what clues do we have thus far that we should definitely include in our box? I'd say that we have definitely this kind of connectivity. I'd say that we have definitely a carbonyl, and we have definitely an OH. Now we should figure out if that's going to be a carboxylic acid OH or if that's going to be an alcohol OH. And so someone that can actually maybe has this and can read it, what is our shift of our OH peak here?
It's like 33. 3350-ish.
All right, so that's where here is like 3350?
Yeah.
Yeah, Hope, you have a question?
Yeah, when you're trying to figure out if it's ortho versus meta, since there's another peak in between 7 and 8 that's not the overlapping signal one, do you not count that? Do you not care about that when you're looking at the ring?
So yeah, we were taking this all into consideration. So ultimately what we would have here is if this is a doublet and a triplet that's overlapped, we would have two triplets, and so that would be this proton and this proton. And then we would have two doublets, right? And so that would be this proton and this proton.
Okay.
So yeah, we're considering all four of those benzene peaks in determining what kind of substitution pattern we have. All right, so let's remind ourselves, let's go back to our cover sheet, which you will certainly have. And so for a carboxylic acid versus an alcohol, which do you think that's going to be? Because I actually can't see it, so which do you think it corresponds better to? All right, we'll go with that for right now. We'll say probably carboxylic acid. Okay. Again, I just literally cannot tell. So probably.
We also know that there has to be an OH, so like it makes sense that it would be connected.
It does, but we could also have a ketone along with an alcohol, right? So that would make sense as well. All right. So IHD. Have we taken care of all of our IHD?
Yeah.
We have, right? So we have 4 from our benzene, and then we have 1 from our carbonyl, whichever kind of carbonyl it is. So let's just take account of what we got left over. So we started with C9H10O3. Interesting. We have another oxygen in there. Okay, so we have used 6, 7 of the carbons. So we have C2. We've used 4. 5 of the protons, and then we have an oxygen left. All right, so let's go back up. Where would you go now?
We can figure out what's left with the carbons and hydrogens.
Yeah, we've got carbons and hydrogens left over, so we look over here, we see, and this is something you should be able to look at and know immediately what you've got. When you have a quartet around 4 integrating to 2 and a triplet around 1.5 integrating to 3. What is it? It's a CH2CH3 next to what? An oxygen, right? Because we've got this thing downfilled around 4. And so, without a doubt, and this is one of those things that you get used to seeing by working these problems, there's really no other way that this would make much sense given, we're not going to go more complicated than structures like this. Okay, so I guess we've used everything, right? And so, I don't know, I think we could end up with 2 possibilities here. All right, so let's see what we can come up with. We've got our ortho substitution. And so if we have a carboxylic acid, I think what we're going to have would be this here, and then this here. Does that make sense?
That's what the answer key says.
Oh, is that what the answer key said? Yeah. I'm trying to think of a good reason to know that it's definitely not Yeah, I mean, why couldn't it be, say, an ester?
That would be too easy. Yeah, we only have an IHD.
Well, I mean, but that's what that is, right? Now we've got the same number of hydrogens. We've got the same IHD.
Will they give you your carbon spectrum and maybe you just don't have enough, like your aromatic carbon can't be transferred?
Oh, I see the clue. All right, so it says, note, there is a signal not shown in the proton NMR spectrum, a broad singlet around 11 ppm.
And that's
What could that be?
that's your carboxylic acid.
That's our carboxylic acid proton peak, and so that's the last piece of the puzzle. So it's definitely going to be a carboxylic acid, so that would be our guy. Things that I think you should put for partial credit. So, you know, now we've got the clue that it's a carboxylic acid, so I would definitely have this in there. And so we also figured out OCH2CH3, I'd put that in there. And so honestly, I mean, if you had this stuff, I'd be surprised if you didn't get the right answer, but if somehow you didn't get the right answer, but you had all this info in the box, I mean, I'd probably give you like 25 out of 30 or something. So, yeah.
So, in the pieces and constraints box and everything, do we have to tell you how we got those things? So, like, for the carboxylic acid, do we have to be like singlet at 11 ppm?
No, I can't ask you to put, you know, the entire thought process in there, because that would take forever to grade, for one thing.
Yeah.
So I'm looking for just pieces, and I'm going to be looking for pieces that correspond to this, or there might be cases such as, you know, what if you had actually put this fragment on there, right? That makes a little bit of sense. I'd probably give a little partial for that, because it's on the right, it's not correct, but it's on the right track. So that just gives me, this basically gives me a chance in drawing form to see your thought process, right? I don't have to read words, but I can see if you've got some fragments that make sense.
So you don't have to write like OCH2CH3 because
Yeah, just show it to me. That's a lot more powerful than writing stuff out. Yeah. Nothing?
Yeah. Is that the only way you can know if it's an aldehyde or a carboxylic acid by looking at the NMR?
Yeah, so as far as we've gotten, you know, to determine whether you have an aldehyde or something else, that's kind of what we're limited to in determining, right? So in a proton spectrum, you typically find an aldehyde proton around 9 to 10. You typically find a carboxylic acid proton around 9 to 13. So that's definitely a big clue. You know, if you go further in chemistry, what you'll find is that functional groups, so carbonyl functional groups, have a very, so we can go more in depth, and you know, there's lots of different carbonyls you can have, and they all have their own sort of stretch that you expect to see. So you might see some exactly at 1720, some exactly at 1740, but that's beyond the scope of what we've done.
But don't they overlap? Does that, if it's just...
Yeah, they do. So in that case, you know, we would expect an OH stretch in our IR spectrum for the acid, right, where we wouldn't expect an OH stretch in the aldehyde. So that would be a big clue. Yeah.
Can we do another spectrum? Like, can we do the one right before this?
Yeah, there are other questions about this?
I'm just a bit, I'm a bit confused, like, how do you know it's enough to sort of get around the legal side of the Is it because of
Mainly because of the integration there, right? So the peak integrates to 2, which means we have to have 2 protons for that signal. So it could be an OH in that case. And furthermore, we don't typically see splitting in OH signals. Those are usually broad singlets. Yeah.
Can I ask a quick IR question?
Sure.
It's on number 6. It's just about that carbon, the bonds like your carbon or nitrogen. Like it's really close, and I wasn't sure.
Which one?
6.
Number 6 on 2014.
2014, number 6.
Yeah, I think there's the next one stuff on the next one.
Okay, so let's see. We have a clear carbonyl stretch in there. So it's definitely not this one or this one. And so furthermore, all right, so we don't have a lot of other information. We do have a peak right here, which is actually very diagnostic for something. Does anybody know?
Well, on our cover sheet, it says a C double bond C is weak and sharp at that exact point, and an N double bond, an N triple bond C is strong and sharp at that point. So, like, what's the difference?
Interesting.
Like, how do you differentiate?
Yeah, so I mean, it's very qualitative. Just looking at this, clearly that's, you know, compared to the carbonyl peak, that's clearly a weak signal, right?
Yeah.
And so I guess we would call that weak. I'm guessing that the answer is D.
No.
It's B.
Yeah.
This teacher wrote some slightly difficult exams. Really?
I just thought it was hard to differentiate.
No, it is, right? I don't know. I mean, I wouldn't do that to you. So, you're welcome. Yeah, I don't.
It'd just be more obvious.
Yeah, I mean, like I said, I try to make things obvious. If you know what you're doing, you should be good. So.
Weak usually means short and strong means strong.
Typically, yeah. So like a carbonyl peak, I would say a carbonyl peak is strong. It's very strong, right? It's almost to the bottom, or you know, it's full. It's definitely a full peak there. I don't know. That's it's interesting. I feel like that's a weak signal, but yeah. So sorry. I won't have to use other people's practice exams for too much longer in my career. All right, Sarah, did you just want to do the one above it?
Yeah, it was like just the one right before the one.
This one, compound B?
Yeah.
Okay, so I'll let you guys work it along with it. So first off, let's do the IHD. So our IHD would be C10, so it's 10 times 2 minus 14 plus 2 divided, so that's 20 minus 14 is 6, 8, 4. And so where's our IHD coming from? Yeah, we definitely have a benzene, right? And so we're told we have 5 protons at 7.2 split into a multiplet. And so anytime you have 5 benzene protons, you definitely have this fragment. So it's going to be a monosubstituted benzene. Okay, so then, let's see, what else? So I mean, here we've got a broad singlet, and then furthermore, we have a broad IR peak.
OH.
Yeah, so that's almost certainly going to be an OH.
So it doesn't matter what number it is on the bottom, like 2.33 versus like 5.
Yeah, the chemical shift of an OH or an NH is really fickle. It's not very diagnostic. I've seen them as low as 1. I've seen them as high as 10. Like, they're just all over the place.
Okay, so just really look for something broad.
Yeah, you're looking for broad. Broad's the really big clue there.
Are they usually weak?
Well, they're going to integrate on a proton spectrum just as one. Right? So we definitely then also have this. And that accounts for our oxygen. So what have we got left? So we've used 6 carbons. So what's left is we have C4. We've used 6 protons. So that's H8. So we just have C4H8. Okay. What's next? I know where I would typically look next. I like to look at the proton spectrum to see if there's anything that corresponds to a methyl group. Do we have anything corresponding to a methyl group?
Yes.
Yeah, so here we've got a signal integrating to 3, and so that makes me think that that's going to be a methyl group. And so it's split into a doublet, so that means it has how many neighbors?
1.
Yeah, so that means it's going to have 1 neighbor. And so do we have any any other proton peaks that integrate to 1? Yeah, so probably what this is corresponding to is the 2.83. Now that's split into a sextet. So that means it has 5 neighbors, right? So we're already showing 3. And so it needs to have 2 more. Alright, so let's think about the possibilities for that. So we could have CH3, CH. We'd have to have something here if it's CH2. It's not really far enough for the alcohol, right? Typically we'd expect that to be more like 4.
Yeah.
Now one thing we do have is we have this peak at 3.47 split into a triplet. And so I'm guessing it's not quite down to 4, but it's definitely de-shielded. So in that case, I'm thinking that we probably have CH2 here. And so this is going to be our peak maybe at 3.47. And so it's split into a triplet, which means it has how many neighbors? 2. And so that would then make this a CH2.
And does the hydrogen on the oxygen doesn't count as a neighbor?
It typically, you don't see splitting with a proton, or an OH proton. All right, so how can we make, I think I see how we can have this make sense. Anyone else?
Yeah. We can connect that to the C, like have a C.
Yeah, so you're saying to basically connect them like that.
Yes.
Yeah, and so if we do that, we've got HO, CH2, CH2, CH, CH3. And so really at this point, we've only got 2 things to put together, right? And so what we end up with is going to be HO, CH2, CH2, CH, CH3, and then our phenyl there. All right, how many carbon signals would we expect for that? All right, so how many carbon signals would we expect from the benzene? It'd be 4, right? So we'd have this one, and then these 2, and that one. So that's 4, and then 5, 6, 7, 8. And so we can go back up here. We see that there are 8 carbon peaks, so that makes sense. Anyone have any problems with that?
How come you can't have a CH2? Like, how come you can't have your ring, and then CH2, C, with an H and a CH3?
So you're saying ring,
CH2, C, with 1 H, then CH3, and then CH2. No, so that would be CH2. And then, no, and then a CH3 below the H. Below the other, on the second carbon. Yeah, and then OH after CH2.
so one thing that jumps out is what kind of signal, what kind of splitting pattern would we expect for that proton? So it's got 7 neighbors, so we expect like an octet. But we don't have an octet for that. We're told it's a sextet. So that's one clue against that. We do have our methyl split into a doublet, and we have CH2s. One CH2 is a triplet, which makes sense, and then the other CH2 should be a quartet. And so that's another one, right? We have this. This would have to be a quartet, but it's we'd expect to see a doublet. So yeah.
Number 5 on your practice problems for the NMR, the April 4th one. On the cover sheet that you gave us, the alkyne is supposed to be a weak signal. But in this, it's really strong, I think.
Which?
Number 5.
Number 5. All right, so I'm gonna go ahead and say I did not make that cover sheet. That is actually the cover sheet from the person that did these practice exams. I think that they might have switched up the strong and the weak signals for the CC triple bond and then the CN triple bond. I think that's what's happened there. Yeah, because here we see clearly what is a strong peak. And so on the cover sheet, we're told that that is a weak peak. Yeah, I'll.
Wait, so what's, okay, so it's sharp. Okay, that makes sense.
It just means not broad, right? So skinny. Yeah, thanks for pointing it out to me. I'll fix that for our exam. I should maybe also tell this professor that I think it's wrong. Yeah.
Can we go to number 3 on 2014?
Number 3 on 2014. A curious chemist. I would also never write that. A curious chemist mixes water. Yeah, so this goes into some physical properties that we kind of skipped over. One thing we can say is that bromoform, which is CHBr3, plus H2O. Can these things react? All right, so first it'd be a substitution reaction of some kind, right? So our halide, what kind of halide is it? No, because it's not connected to carbons, right? Yeah. So yeah, you're right. It's just it's a methyl, really. And so I mean the technical name of this would be the IUPAC name would be tribromomethane. So we have tribromomethane, and so that screams, yeah, we can do SN2, but then it's water. And so can we do SN2 with water as our nucleophile? No, so we'd have to do SN1. Can we do SN1 at a methyl? No. So I think what would happen is we would just continue having tribromomethane with water, and so those should form 2 layers. Yeah, and so then the question is which is going to form the bottom layer, and so that's just dependent on basically if you have halogens on your organic layer. So if you have halogens on your organic solvent, that's going to be your bottom layer. If you don't, then it's almost always going to be the top layer. So in this case, we do have halogens in our organic structure, and so we would expect the bromoform to be on the bottom. I sure hope it's A.
Yeah.
Okay.
So halogens go on the bottom layer?
Yeah. Yeah, anytime, so like chloroform, if you ever have a chlorine or a bromine, just any halogen on your solvent, then when you're in lab and you say are using a set funnel, you're going to find the organic layer to be on the bottom. Got this?
Yeah.
Okay.
Could you say that it's because it's a heavier molecule that's why it's on the bottom?
I mean, no, because ultimately it's going to be dependent on the density, and so it's not a like a molecular property. It's more like how they interact as a whole, right? How dense they are as a whole. Now, it's certainly related to the fact that bromine is a big atom that weighs a lot, so we can pack more stuff into a space, but I don't think it's always going to be the case. Density isn't always going to follow the molecular weight of something. So, yeah.
Because we kind of skimmed over that, like the questions like that one.
What do you think?
No. I'd be like, well, a lot of children suffer.
No, that doesn't sound like me. Priya?
Could we do a couple on number 7 of the 2015 exam?
2015, number 7. I did this already. Yeah, so we can just kind of walk through them. The top one has light in it, so it's clearly a radical reaction. And so we're reacting HBr with peroxides, and so it's clearly going to be an anti-Markovnikov addition of bromine. So that's what we've got there.
Just like the last two on there with like the plus and anti, that's just because with the two CH3 sun and chiral.
Right.
And then the third one, we just had a shift, like in the answer key, it's on the second, instead of being on like the third carbon on that chain, it's on the second. That's just because of a shift.
Yeah. Yeah, and so what you could also have is if you're going through an SN1 mechanism, And see, when I write exams, I think it's a little much to expect you to give me the major product, but assume that there's a shift in there. Because in reality, the shifts always give lots of different products, so it's sort of hard to really know which is going to be major. But in this case, yeah, what you could do is you could end up with alright, so you have this cation, and so you've got protons here. You could do a 1,2 hydride shift.
And that would just bring it closer to the
Yeah, so you'd end up with the so what, I mean, is there a thermodynamic reason for this shift to happen?
It's a little bit more stable, right?
Oh, it's not a little, I mean, it's way more stable.
Closer to the
Resonance?
Yeah, because of resonance, right? So here we have a cation where there's no resonance, but if we move that cation over in the shift, we end up with a resonance stabilized cation, and so there's a huge thermodynamic reason for that to happen. And so from there, we would expect the product having added to that benzylic carbon closer.
Thank you.
Yeah.
Just for like visual help, can we draw the resonance structures of that more stable carbon-cation?
So this would be one.
So you can just do one arrow, like one arrow moving the entire
Yeah.
double bond.
Totally. Forgot our charge. Charge is there. And finally, and so that's why that's so thermodynamically downhill, is because that's an incredibly stable cation there. So yeah.
Can I ask a question on this?
Are there any questions related to this?
Alright, can you do number 6 on this example?
All right, this one right here? Okay, so for each of the following sets of reactions, determine which of the choices would react the fastest. Okay, so let's see. In this case, we can look at our reagents. Our reagents are, it's a negative SH, indicating that we could go through an SN2. We've got a great nucleophile. And so if we have a nucleophile that would love to go through an SN2 reaction, do we have anything on the left side that really wants to go through an SN2?
C and A.
Yeah, so C and A both would. Blue definitely would not, because it wouldn't be a good leaving group. And so we're actually going to talk a little bit tomorrow on the difference in leaving group ability of the halogens, but ultimately what we're going to find is that iodine is better. And it's just a pKa argument. So HI, the pKa is like -9. HCl, the pKa, I don't know, more like -6. And so what that tells you is that this is a stronger acid because iodine is more stable by itself, and so for that exact reason, we expect iodine to be a better leaving group. But, I mean, really, they're both awesome leaving groups.
So are we gonna have a PKA?
Yeah. Yep.
The size of the carbon is nucleophiles, it doesn't matter for leaving.
What's that?
Like the size of the atom doesn't matter for leaving.
Size is for nucleophilicity. Yeah, and so size ultimately has an impact. Size is the reason that iodine, that HI is a stronger acid, because the negative charge is more stable spread out over a big atom versus a smaller atom. But size is specifically different in nucleophilicity, and that has to do with polarizability, and so, yeah. Those things kind of get gray area a little bit. All right, so then the next one, our nucleophile, SN2 or SN1?
SN1.
SN1. We can't do SN2, so we have to do SN1. And so what's going to be the more stable substrate to go through SN1?
A.
Why A?
Or no, C, because of resonance.
Yeah, so here we got tertiary, here we have secondary, here we have allylic. And so ultimately the rate determining step is going to be determined by how easy it is to form the cation. And so in this case, an allylic cation is going to be the most stable. So that's going to be the substrate that reacts fastest. So then for part C, SN2 or SN1?
SN2.
Yeah, so we can do SN2, so we should try to do so. So what do you think, A, B, or C?
B is less substitution.
Yeah, so least crowded. They're all secondary, and so if they're all secondary, the methyl groups that are going to cause crowdedness here, they don't have to be connected to the carbon that the bromine is. They can be nearby. It's still going to be more crowded. So, yep. Yeah.
Why is it not?
Because it's not a good leaving group, and we'll talk about that tomorrow. We'll finish that up. Paul?
Did we go over the last one on the 15 again?
This one? Okay, so we've got 4 benzene protons. That tells us that we're going to have a disubstituted benzene. And so furthermore, we've got a singlet, 2 doublets, and a triplet. So that is screaming out a certain substitution pattern.
OCH2, CH3.
No, for benzene.
Oh. The meta.
Yeah. And remember, you don't have to know the ortho-meta-para names. But this definitely is telling us that we've got meta, because we would expect a singlet, a doublet, and a triplet here. And so, yeah, that looks pretty good. All right, so our IHD is going to be 9 times 2 minus 9 minus 1 plus 2. So that's 18 minus 9 is 9 minus 1 is 8 plus 2 is 10 divided by 2 equals 5. So we've used 4 of our IHDs up in this benzene fragment. So that's anytime you have a benzene fragment and you know the substitution, I would definitely include that. That's a big chunk of partial credit right there. All right, so now Sarah, you can tell me what the other part is.
You have the OCH2CH3.
Yeah, so again, we've got that very, very, very common pattern where we've got a quartet integrating to 2 around 4, and then a triplet integrating to 3 that's much more upfilled. And so what that's going to be, it's going to be an O, CH2, CH3. So, what's left? We have, so a C9, we've used 1, 2, 3, 4, 5, 6, 8. So we have a carbon left. It was H9, so we've used 1, 2, 3, 4, 5, 6. We've used all of our hydrogens, is that right?
No, it's H. Oh.
Yeah, so we have an oxygen and a bromine left? Is that all we've got left? So that's all we've got left. Interesting. Okay, so we also have a unit of hydrogen deficiency left. There's not a lot of ways we could really do this, right?
I had it as C, like as a carbonyl and then a bromine.
Yeah, I mean, so the only way we could add a unit of hydrogen deficiency here is going to be a double bond between carbon and oxygen, right? Oh yeah, and so here, there's the key clue there, is a peak at 1720. That's absolutely a carbonyl peak. And so, in this case, we'll have that, and then this must be a bromine. I don't know where else our bromine could go.
That's not what the answer key says. Has the bromine directly?
Oh yeah. All right. So So there's 2 possibilities here. Yeah. If I see what you're saying.
That's the part I didn't understand.
All right. So we've got one possibility being this, which apparently is incorrect. So the other possibility could be COCH2 CH3 with our bromine here. All right, so let's get to work. How do we know versus the other.
I think it said you could get credit for either one of them.
Oh.
Oh. Wow. There you go. Yeah, I don't see, I'm trying to think if there's anything that we haven't learned that could point to why. What's that?
Is there anything special about the components that might?
No, not really.
It says IR through carbonyl stretching frequency.
Yeah, you could definitely, so like I said, we say that a carbonyl is 16 through, or it's about 1650 through 1800, but you can find entire tables of just carbonyl chefs. So an ester might be 1720, a ketone might be 1740, a carboxylic acid might be 1760. So certainly seeing where exactly this stretch corresponds to will tell us whether or not is this ester carbonyl or it is this acid bromide carbonyl. We'll learn about that in Orgo too. So that's how you would tell. We don't have the information. So. Yeah.
And you can tell right away that there's no, like, when you look at your peaks for the IR,
Yeah.
you can tell that it's not an OH because it's not.
Yeah, we just don't have an OH peak.
And is that also, like, in order to have an OH, do you also need an HNMR shift of like 10?
So you're talking about an alcohol?
Yeah.
So the alcohols can be anywhere pretty much.
But, or, I'm sorry, to have a what's it called? To have a CO, like a CO2H.
An acid, carboxylic acid.
That would need an H really, really low.
Yeah, that one typically I think shows up, but not all OH and H bonds even show up. So you can't. They're not that reliable. Yeah.
Is this about the level of difficulty that you'll have on the exam? Are they a little bit harder?
Yeah. You know, honestly, if I fretted over anything writing this exam, it has been trying to figure out what is the appropriate spectroscopy problem to put on there. And so I think they should be similar. You know, it's really tough, I think, for me to find the middle ground. But I think you know, I'm actually still deciding. So.
Okay, so they're not going to be like crazy difficult.
I'm not going to put anything more difficult, I don't think.
Okay.
Yeah. So. It's hard because there's like limitless possibilities for molecules to put on there. And so I don't even know where to start. Yeah. Yeah.
Is a Lilith radical more stable than tertiary radical?
A Lilith radical is more stable than tertiary
And
radical.
same with carbocation?
Yes, same with carbon.
Like secondary or primary, or like any or
Pretty much, if you see resonance, you can assume it's more stable than any non-resonance stabilized carbocation or radical.
And then you said both like compared a two parallel like to like a 3' but it's like the same stability.
So if you have a secondary allylic versus a tertiary allylic, you would expect the tertiary to be more stable, right? Just because now the resonance is going to be the same, and so we've got a little substitution that could make a difference.
Tertiary or secondary just tertiary, but I don't know. I guess that's what you're saying.
Yeah, I mean, if you look for the similarities, I mean, you've got to choose one based off of differences, right? And so if they're both allylic, that's not going to be the deciding factor. So in that case, it would have to be substitution. Yeah.
Speaking of like hard spectroscopy problems, some of the ones in the textbook were like kind of.
Oh, the textbook ones were brutal. Again, I hate this textbook
Okay,
so
we
much.
like couldn't get them, should we just not?
I'm not too. Yeah, some of them were chiral examples. Like, I don't
We're
know.
not gonna have chiral.
No, I'm not going to put anything chiral. Not at least for interpreting spectra. You know.
So what about antiotopic stuff?
Uh-huh.
Are they going to be on this?
Yeah, that's fair to but I'm not going to put that into like one of the interpreting spectra problems. You know, more likely that would be a specific problem or a question that
What would
I
a
asked.
question like that be like?
How many signals would you expect for these two protons?
The original question.
What?
Could you repeat like the original?
It was about like an antiotopic versus diastereotopic. So that's the one where basically we have to do the replacement rule.
Oh, the DH.
or the replacement test. Yeah, so you switch one to a deuterium, and then the other to a deuterium, and see what the relationship between the molecules are.
Is there a way we could like do a practice version of that?
Yeah.
It would be nice, actually.
And in fact, there's another one called homotopic that we didn't get into. So we're just looking at enantiotopic and diastereotopic. So, you know, for example, let's see. I don't want to do that one. Let's see. All right, so we have proton, proton. How many signals would we expect from those two protons specifically? So I'm only asking about these two. Why two?
Because they're diastereotopic.
Yeah, so they're definitely diastereotopic because we have, if we replaced one, we would get deuterium here. If we replaced the other, we would get deuterium on a dash, and so those are clearly diastereomers. And so what we have are diastereotopic protons, and so that means that for those two protons we would see two signals.
And why do you see two signals?
You see two signals because they're just literally in different chemical environments, and so you can prove it with, say, a Newman projection. So, you know, looking down that bond, so let's say that you have a Newman, and then we've got our bromine on a wedge. This is actually, if I'd had more time, I would have liked to have drawn this out in class, but I didn't get a chance to. Okay, so let's say we have this diastereomer, and so the deuterium, so for example, let's put the deuterium through the or actually, we don't have to worry about it. Let's just say anytime that we've got the proton between the bromine and the methyl here, you can see that the methyl has to be next to the other bromine, right? It has to be. So if we have our proton with this relationship, you can see that the methyl is next to the bromine. And so what happens if we try the other diastereomer, and so that's going to be, and ultimately this is why we get two peaks, is exactly right here what I'm drawing. So the other diastereomer, we switch our H and our D, and so again, what we want to do is we want to put our proton between our bromine and our methyl. So we'll do a little rotation.
Why do you want it like that?
Because we're trying to see if we can ever have this molecule look just like the one on the left.
Okay.
Right? Because ultimately what we're talking about are these two protons, the H and then presumably that D there, right? And so if we try to basically come up with this exact conformation, and that would be necessary if these are going to be chemically equivalent, right? They have to be able to experience the same exact chemical environment. So when we put our proton between our methyl and our bromine, what has happened to that other methyl?
Now it's next to it.
Yeah, now it's no longer next to the bromine. And so ultimately what we find is that one of these protons can exist in this conformation on the left, but the other can never exist in that relationship, because now we see that these two conformers, they must be different, right? And so basically, because they're diastereomers, we can never have this exact conformation in this molecule. And because we can't have this, and in fact, none of the conformations will be the same, that's why diastereomers have different chemical and physical properties and also end up giving different peaks on the NMR spectrum. It's because, well, this proton is never going to be in this situation where it's between the bromine and the methyl, and then over here is its methyl. It can only be in this situation, which is chemically inequivalent.
So you would see two separate peaks.
Yeah, so we definitely see two different peaks in this case.
But we wouldn't have to interpret an NMR spectrum like that.
No. no, but.
And if they were enantiomers, they would have this would be one peak.
Yeah, what we find is enantiomers, because their mirror images actually can exist in the same exact conformation, it's just reversed through a mirror, right? But still, it can't have the same relationship. And so that's why enantiotopic protons are actually in the same chemically equivalent environment. Yeah, no, I think this is a really good way to show that. I just didn't have time in class to draw elements.
In the beginning, you said like with the NH2, you would see like the stretch where it would be like two different like signals for that. But
Yeah.
if you were just given numbers, is there any way to tell that you have?
I mean, I'd have to let you know, right?
Okay.
You've taken my exams. I'll be clear. You'll know what I'm getting at. Yeah.
Well, we have to do some of the things in the textbook had chair conformations and how reactions affected them. Will that be?
No, we'll do some of that when we go to elimination reactions.
So there won't be nothing will show up in a chair on the exam.
I mean, if I put any six-membered cycloalkane ring, it's presumably in a chair, right?
But we won't have to show the chair.
Yeah, I don't think that in your analysis of what product would form, you'd ever need to consider the chair. Yeah, we'll talk more conformationally with elimination reactions, where the chair actually has a pretty big impact on reactivity, but not for substitution reactions. Yeah.
Would allylic halide and SN2 be not as favorable as like normal halide? Because they'd be more crowded.
So allylic halide would actually be less crowded than all right, so basically if we were comparing this structure versus this structure, which one would be more crowded?
The without the double bond.
Yeah, so this is actually more crowded because when you think about, and this totally threw me off when I was coming up through the ranks, right? Because if you just look at these look at these structures, you think, well, there's another line right here. Clearly, that's more crowded, but in reality, it's just because there's more stuff around this one, right? So we've got 2 carbons and 5 protons. Here we've got 2 carbons and 3 protons. And so this is planar and flat, where this is 3-dimensional and bulky. And so, yeah, this is going to be more crowded because here we have an sp3. The bond angle here is 109, where the bond angle here is 120. These protons are, by definition, they have to be closer to this carbon. So, yeah, ultimately, sp3 is typically going to be more crowded than sp2, which is and that's why when we say something like, we could compare it furthermore to, this is poorly drawn, but if it was sp, well, in this case, that's just a carbon, right? And so this would be the least crowded because off of this carbon is nothing but another carbon. So, yeah, the more bonds there are, typically the less crowded it gets. Yeah.
When we're looking at nuclear files, will the charge always be shown, like for example, if it's on an oxygen, or will we have to know whether it's a charge?
You'll need to know, but it's not that tough to know because usually you'll see something like sodium methoxide. And so, where could the charge go? It can't be on the carbon, it can't be on the hydrogen, it has to be on the oxygen. There's only one place, right? So if we have a negative charge, typically you'd see it like this. Or I could, if I gave you a structure like this, so let's say it's sodium cyanide. Sodium, has got a positive charge, which means you're going to have a Cn minus structure here. And so let's see, we'd have 4 valence electrons, 5 valence electrons, and then a bonus electron from the minus charge. And so ultimately, let's see, we could have, I guess, a structure that looks like this, but probably not, because that's electron. All right, there's not enough. There we go. So does that even make, let's see. Yeah, so we have this structure with the negative charge on the carbon. I guess I don't know. I think that's it. That's the only structure we could have. So you have to have.
Would it be better just to memorize what common things are for SN2 and SN1, or?
Yeah, and I mean, honestly, the only thing I gave you for bad nucleophile was neutral oxygen, right? So the big thing is to notice if you've got just methanol instead of methoxide, you don't have a good nucleophile. Oxygen Oxygen's important because oxygens are everywhere in organic molecules, and so we need to know exactly how they react. But, and I might mention a little bit about this tomorrow. What you could do is if you have, say, methanol. So if you just had methanol, you have a bad nucleophile. But what you could do is react it with something like, say, sodium hydride, which is a strong base. And so then you're going to deprotonate to basically give that. So now you actually have a strong, and this is synthetically how you do it. If you need to add methanol to something, you would react it with base to give you methoxide, and then you would add that to your organic thing. We'll talk about that a little bit, I think. We should have time. All right, really last questions. My wife is expecting me. Yeah.
What's a neutral oxygen?
It's just an oxygen that doesn't have a formal charge. Yeah. Sarah?
There was